So we have the welcome, happy Friday. We have started on chapter 2. We got 2.2 where we looked at how to evaluate limits numerically with plugging in values really close and um graphically of actually looking at the graph, see what happens. And so you have that second written homework due today that uh, so if you haven't gotten that to me, I've gotten most of them. And then post-class activities, we have one assigned Wednesday that's due today. And Wednesday we talked about limits. And so that one's gonna be about the things we talked about. I believe it was one of those plug in 6 values really close and evaluate it. And then there'll be one assigned for today. That's going to be using our rules of limits. And then also posted today was written homework 3 that has, again, 6 problems. 3 from what we're doing today, 1 for Monday and 2 for Wednesday, just by what good problems there were. But we have that. That will be the last written homework before the exam that will be coming up on February 9th. So any questions on things as we get going? If you have homework stuff that you haven't given me, I'll
Sorry,
go.
that went long.
Yeah, I was hearing that you've made it. I'll leave those posted for just a little bit longer and let you guys get stuff if you have it, don't have it. If since it was forgotten, if you can take pictures and send it to me as soon as you get them. It might have a point off for like late, but I'd rather have it than nothing. Yeah. Yeah. When you get home, take pictures, send it to me. Because I'd want to grade it this weekend if at all possible. Yours too?
Forgot to ask about. Yes.
Is there something we need to want to look at or?
Yeah, it was something that I don't think I did it right, so I started, but um, would you be willing to do a little bit of domain and range? Because I'm a little confused.
Okay. Was that? I guess that was on homework.
It's not the
2.
unit problem.
Oh, the unit problems. Yeah, absolutely. Was there any in specific for us to look
Um,
at?
if you like me to, I can find a specific one.
I mean, I can look as well,
There's
largely looking at section. Yeah, there should be a fair amount.
1.3.
1.3 has them. Okay.
Like, okay, I can't.
Okay. Okay, so we want to look at domain and range stuff in 1.3. Let me see if I can find some.
Here's.
Thank you. Add that to this pile. Make sure we count those. Okay. 1.3 domain and range, finding the domain and range of a function. Okay. So finding domain and range largely comes down to there's 2 big things. One, for domain, there are the rules. Let me unfreeze what I'm. Where did the remote go? For finding domain, There's two big rules. We can't have a negative under a square root. And we can't have 0 in a denominator. So looking at a few of these, look at 17 real fast, which is at g of x, I'll call it f because I've already started writing that, equals the square root of 6x. I can't have that become negative. So what x values would make 6x negative? Any negative numbers. So the domain here would be, I could put in 0 because I can take the square root of 0. 6 times 0 is 0. Square root of 0 is 0. That's fine. And I can plug in anything bigger than 0 because 6 times 5 is 30. And while the square root of 30 might not be a decimal I know off the top of my head, I know my calculator will give me an answer to the square root of 30. But if I plugged in like -1, I'd have 6 times -1. Square root of -6 doesn't exist. Well, isn't real. We don't want, for domain and range, we want real function values, and the square root of -6 would be not real. And any negative in there. And then range, for a lot of them, there's a few different rules that come about. But a lot of them are knowing the general shape of the graph. So like the square root function, here's my x, y one. This is what the square root function looks like. It just keeps growing. If I put scaling to this, this would also be the square root of 6x. Just keeps growing as we go. So the range is actually the same. Square range 0 to infinity as well. But then looking at something like the next one down that looks very similar, 19, has f of x equals the square root of 16 minus x squared. When I want to ask the question, what's going to make that under the square root negative, I need to think about things like what's going to make that 16 minus x squared 0. So that's the question. What makes 16 minus x squared equal to 0? What x values would do that? 4. Is there any others? -4. Is -4 squared is 16? 16 minus 16 is 0. So I know right now I can plug in 4 and -4 because the square root of 0 is 0. I get an output there. It's now a question of what can I plug in between? Can I plug in something smaller than -4? I think about 5, -5, sorry, 16 minus -5 squared. That'd be a positive number or a negative number. -16 minus 25. I'll write out what I say. If x is -5, I'd have the square root of 16 minus -5 squared. I don't really care what that number is. It's -9 under the square root. But all I know is there's a negative. That can't happen. So I can't have something smaller than -4. But I do know -4 works. Let's look at something between 4 and -4, like x equals 0. If I plug in x equals 0, I'd have 16 minus 0 squared. Can I take the square root of 16 minus 0 squared. Yeah, that'd be the square root of 16. That's the square root of a positive. That's okay. So I can have things between -4 and 4. So I know I'll at least have that. And now check, can I plug in something bigger than 4? Plugging in something bigger than 4 would be the same thing as this. I'd have 16 minus 25 or 16 minus 36 or 16 minus something bigger than 16. And I'd get a negative under the square root. That can't happen. So the domain is -4 to 4. I'm going to try and write domain over on the other side. I made a comment for 17 of finding range is often coming down to knowing what the shape of this graph is. And we looked at a problem similar to this when we went over 1.3. If I write y equals 16 minus x squared, square root, how do I get rid of that square root? Square both sides. Y squared equals 16 minus x squared. And if I move this x squared over and had y squared plus x squared equals 16, what is this graph?
Circle.
A circle with radius, what?
4.
4. When we take the square root, we're getting just the top half of that graph. We're getting from -4 to 4. Okay, that was the domain. And how high would this go? Where would it be crossing that y-axis?
4.
4. So the range, what y values are we hitting? Where if I scroll upwards, I start hitting at the x-axis, which is y is 0, and we stop hitting at 4. So the range would be 0 to 4.
Oh, are we allowed to use like Desmos to look at the graph to see what the range would be, or?
Yeah, you'll have access to calculators. I would say make sure you're justifying, like maybe if you're using that sketch it to say, hey, this is what I was looking at to find the range. But yes, you can definitely look at those graphs to figure them out. A lot of times, I mean, that's the helpful thing there. I want to look at one more, 23, that only asks about domain. I am grateful for because finding the range would be complicated without a graph. '23 asks for just the domain of the square root of x plus the square root of 1 minus x. So this here is asking the question, 1, what x values can I put in here? What's the domain of this? What's the domain of this? And where do they overlap? So what x values could I put into this first one?
0 plus 3.
0 to positive infinity, just not anything negative. What could I put in here? I'm gonna write out an inequality. I need this to not be negative, meaning I need it to be greater than or equal to 0. How do I get x by itself? Take what to the other side? The 1 by subtracting negative x is greater than or equal to -1. Dividing by the negative will have x and 1, but something happens with inequalities when we divide or multiply by a negative. It flips the sign around. So x has to be something smaller than 1. This notation means the domain of the second part is -infinity up to 1. Those are the values I could plug into the second square root. And now the question is, where do these two things overlap? If I put these both on a number line, the red, nope, that's not the red. The red goes from 0 to infinity. The gray goes from negative infinity up to 1. A little messy there, but where do those overlap?
0 to 1.
0 to 1. That is the total domain of f of x, because anything between 0 and 1 can both go into the square root of x and the square root of 1 minus x. It will be the one interval where both of those square roots we get a real value for. So the domain here is 0 to 1 for the whole function. Are there any specific other ones wanting to look at? Just I picked some random domain ones. Does that help clarify some domain and range? Domain is the x values we can plug in. Range is the y values we can get out from the function. Range often looking at the graph. Even domain looking at the graph can help. The one warning would be that graphing windows don't always show the whole picture right away. So just making sure you are checking the whole graph as much as possible. Any other things we want to look at? 1.5. Any specific problem there? 51? This is the cost you needed. Is that the... Okay. I'm going to close this and reopen it. Neat. The question was 1.5, number 51, which is you need a total of 50 pounds of two commodities costing 1.25 and 2.75 per pound. So 50 pounds costing 1.25 and 2.75 per pound. Verify the total cost is y equals 1.25 x plus 2.75 50 minus x, where x is the number of pounds of the less expensive commodity. So this ultimately is coming down to just, again, like a verify of what are we trying to get. We're trying to get that if I take a 1.25 times some amount plus 2.75 times some other amount, I'll call it B. The total cost, this will be what our total cost is. But I have 50 pounds total, meaning x plus b has to be 50, or b is 50 minus x. And so they then trade this out to be a y, or sorry, no, they don't trade it out to be a y. But they say confirm that this is our total cost function. Total cost is 1.25x plus 2.75, 50 minus x. So y equals that, verified. Find the inverse function of the cost. What does each variable represent in the inverse function? B, when I have this 1.25x plus 2.75 times 50 minus x, we want to combine like terms. This is just a linear function. Combine like terms and get x by itself. So I'll just give that step. This is then switching our x and y's, ultimately. The inverse function switches the x and y's, meaning my total cost becomes my input, and my output will then be the less expensive, or sorry, the number of pounds of the less expensive commodity. It switches that input and output. The domain of the inverse, the domain of inverse is range of original. So for C, you want to think about what that range of the original would be. How many pounds of the less expensive commodity could we have? Well, we can't have more than 50 pounds, and we can't have fewer than 0 pounds. Plug those in to find the range, and that would be the domain of the inverse. And then D, determine the number of pounds of the less expensive commodity purchased when the total cost is 73. That's set this equal to 73 and find x. Or plug 73 into B. Either way, D, plug 73 in for total cost. So there are some steps to help guide. If there are more follow-up questions on that, be glad to look closer, but just want to give some steps to start. All right. There were some with that. Gonna actually get into today's of Wednesday. What did we do Wednesday? We were looking at the numeric and graph versions of finding limits. And we got a limit is saying limit as x goes to c of f of x being L means when we get arbitrarily close to, or as we get arbitrarily close to C, our outputs get arbitrarily close to L. No, we get very close to L as our x values get very close to x. That was our, to C. That was our kind of loose terms definition. There was a formal one with epsilons and deltas, but it's just as I get really close to an x value of C, my outputs get really close to an x value of L. Besides looking at these from just a graph or numeric perspective, we want to be able to do them, one, really quickly for other purposes that we will get to, and two, there is a pattern to them. There are rules that are happening that we want to look at. We had the example of the sine of x oscillating one, the sine of 1 over x, that oscillated really quickly. And one of the things we saw on Wednesday was if I picked out specific values, it can look like the limit might exist from one side or another. So numerically, it depends on picking good values. So not always the best route to take numeric. Graphically, the whole point of us starting with the graph version is that computers are so fine with their pixels, we might not even see a point not existing. So we want to be able to do this analytically or algebraically so that we can verify these limits for ourselves without depending on picking the right values or looking at a graph to do so. So some first basic limits. One, if I am taking the limit of a number, my function is just a number, then the limit is that number. So one of those, if my function is a number, I don't care what x is, it's the number. If I'm taking the limit as x goes to c of just x, that's a line, y equals x, I can just plug in that value I'm going to, c, and get c. And then we can also take a power of a limit, and that results in us just plugging it in as well. So actually looking at some examples. If I'm looking at the limit as x goes to 3 of 2, this is my function. What does the function y equals 2 look like? Yeah, it's a flat horizontal line. So no matter what, at 3, from the left-hand side, I approach 2. From the right-hand side, I approach 2. The limit is 2. So there's a graph of why that limit comes out to be what it is. But the rule is, if I take the limit of just a number, it is that number. The second rule, if I'm taking the limit going to a number of the function x, I mean, what does the function x look like? What does y equals x look like? That line, yeah. Pretend that went through the origin. As I approach -5, that's not where -5 is. As I approach -5, well, from the right-hand side, I'm approaching this value, y equals x. I'll be approaching -5. And from the left-hand side, visually, I'm getting close to -5. From what we did Wednesday, that means the limit is -5. And the last one is saying we can just apply that rule with a power on it. So I'm not going to draw a graph for this, but I will just walk it through of limit as x goes to 2 of x cubed. I can just plug in 2. And my limit will be 2 cubed, which is 8. So there's some first basic rules, and we'll get some more as we keep going. Here is a bunch more properties. They look, when we get these long lists of properties, they often are a bit of, wow, it's a whole lot of very complicated letters and things going on. But this list of properties essentially says limits behave exactly as you think they would, as in they behave just like plugging in a function, essentially, unless I divide by 0. So if I already know certain functions, if I already know certain limits, I can multiply by a constant. I can add 2 functions together and take their limit. I can subtract them. This list is just, they behave like we expect them to. There is nothing surprising that ends up happening when we take a bunch of certain limits. Addition, subtraction, multiplication, division, powers, nothing surprising happens. So looking at an example, limit as x goes to 3 of 5x squared minus 4, said nothing surprising happens unless I'm dividing by 0. What that big list is saying. Am I dividing by 0? No. So I can plug in 3. So this just says I can plug in 3. What would I get if I plugged in 3? Should be 41. And even if I am dividing by 0, they continue to behave as we would expect them to for the most part. If p is a polynomial function and c is a real number, then the limit as x goes to c of p of x is c. That is what we just used. Where if I'm looking at a polynomial where there's nothing, no x's in a denominator, I can just plug this number in and evaluate it like I would evaluate a function. A rational, same thing happens. The only thing I have to worry about is I don't divide by 0. The denominator is not 0. So, as an example, limit x goes to 1, x squared plus x plus 2 over x plus 1. If I take 1 and I put it into the denominator, what does that denominator come out to be? I plug 1. It'd be 2. 2 is not 0. So I can just plug it in. 1 squared plus 1 plus 2 over 1 plus 1 is 4 over 2, which is just 2. Limits behave how we expect them to unless we divide by something weird. So a radical. If I have a radical involved, the limit will behave exactly as I expect it to. As long as I'm not taking the square root of a negative number. That's what that sentence says. So, limit x goes to 9 of square root x. What do you think that is? The square root of 9, which is 3. Okay, limit of composite functions, which I think one of these style is the one you're asked about. But if I am composing functions together, I can take the limit of the inside and then plug that into the outside, as long as they are nicely continuous. How this often works is that I'm given things like the limit as x goes to 3 of the cube root of 2x squared minus 10. This is a hidden composition of functions. I have 2x squared minus 10 inside the function of the cube root. Basically, it's saying my composition rules, all those rules before, I can combine them together. Nothing weird happens when I combine all my rules together. So, what would I do to find this limit?
Plug in 3.
Plug in 3. The cube root of 2x squared minus 10, plug in 3, I get 2 times 3 squared is 18 minus 10 is 8. What is the cube root of 8? This can be phrased differently, so I do want to look at a phrasing that also comes up if I can find an example. My apologies, we can get that at a later juncture, unless you can reach it. Thank you. Put it back so I don't do that again. Suppose f of x is x plus 7, and g of x is x squared. If I want to find the limit as x goes to -3 of f of x, what do you think that comes out to be? Plug in -3 to what? The f of x. So -3 plus 7 is 4. What if I want to find the limit as x goes to 4 of g of x? 16. 4 squared is 16. And then last one. No just kiddings today. X goes to -3 of g of f of x. This is a new phrasing. This is another phrasing we can use of this rule happening. So this rule is saying, let's look at the inside limit here. Limit of f of x. I already found what that was. Well, limit of f of x was 4. So I'll write out what I'm saying. G of limit x goes to -3 of f of x was 4. That's not where I want to write that 4, but we get the point. G of 4 and g of 4 we also already found. Is that I can evaluate the inside limit and plug that in. Limits, unless something weird like dividing by 0 happens, are going to behave exactly as we think they will. So, limits of all the transcendental functions. The transcendental means trig and exponentials. And technically all the polynomials as well. All our basic functions. All of these, there's a whole lot of writing here. They all say plug in the value like we would a function. But there's a sentence up here that says as long as it's in the domain. As long as we're in the domain, we can just plug in the value and get the output. Which, being in a domain, what is, from earlier, what can we not do, or what are the 2 rules of what can't happen for finding that domain? We can't do what with a square root? Have a negative under a square root, and we can't divide by 0. So I've been saying limits act as we expect them to, as long as we're not dividing by 0 and technically taking the negative of a square root. So the limit as x goes to 0 of tangent of x means plug in 0. What is tangent of 0? Not 1.
0.
Okay, it is opposite over adjacent. It is also sine over cosine. What is sine of 0? It's this point here. Sine, the y is going to be 0. The cosine is 1. The x coordinate is 1. 0 over 1, 0. So tangent of 0 is 0. So the limit as x goes to 0. It might be a spot to actually look at a graph real fast. Because all of them are having this type of thing. But here is tangent. Let me make that bigger. Nope, that's not making it bigger. All Wednesday we talked about looking at graphs and numerically of plugging in values. But looking at a graph, as my x gets close to 0, what is that y value there? Surprising. 0. It's crossing 0, 0. That is what we just wrote out here. This fact that it's crossing 0, 0, what this problem right here is saying. Limit of sine squared x as x goes to 0 means we can plug in 0. So what is sine of 0? 0 squared, 0. But not all trig functions are 0, just all these ones apparently. And e to the x behaves the same. I can just plug it in. As long as I'm not breaking domain rules, I can plug in that value. So plug in -1 e to the -1. Also could be written as -1 over e. Okay. What do you think about 4? How would we go about evaluating that limit? Let me zoom in. Yeah, what have we been doing?
Is that 3?
Okay, how are you getting 3?
E and ln. Easy.
Yeah. So we want to plug it in, ln e to the 3rd. And ln and e cancel, yes, but we have to be careful that we don't just say that's 1 cubed. What does natural log do with exponents?
It brings 3 down.
It brings it down. So we have 3 natural log of e. Natural log of e cancel each other. So yes, it is just 3. But it's from those natural log of e rules we got on Monday. Okay. Now is where we start worrying about what if we are dividing by 0. So let C and a real number, let C be a real number, and let f of x and g of x be the same function everywhere except C. Or at least nearby to C. If the limit of g of x approaches C, then the limit of f of x also approaches the same thing. Okay, what this one is all those functions I showed where we saw the graphs, but then there was this little undefined spot. We're trying to find the hidden function in the background where that little spot isn't undefined. What do I mean by that? Oh, where is my limit one? Here's my limit one. Want to look at G. Okay. G, golly, G is this x squared minus 1 over x minus 1. What does this graph look like? Looks like a line. What slope does it appear to have? 1. And what y-intercept does it have? 1. It looks like the function x plus 1. And can't really be seen, but that red and purple are now right on top of each other. They look like the same. The issue is on G, if I look at where 1 is, it tells me it's undefined. If I look at H, and I look where 1 is, it actually gives me a value. Gives me 2. The task that this big theorem is stating is, can we figure out that function that's the same, but actually defined at that point? And what these ultimately come down to are simplifying rationals. So x squared plus x minus 6 over x minus 2. If I take 2 and plug it in, what happens in that denominator? I divide by 0. We don't like dividing by 0. Limits now act differently than we would expect them to. We can't plug in 2. So we have to figure out a way to get rid of that x minus 2. If we can, we want to factor the numerator. I don't remember how that numerator would factor. We are not anymore in the zeros.
2.
It's going to look like x, and there's going to be numbers there and there. That's what factoring is. What are these parentheses I can fill in?
And then I just started going on. This is that's the next thing. That's
Sorry, what? Okay, so factoring review real fast. If this number here, sorry, not that number. If this number here is a hidden 1, we're going to look at this negative 6 and ask, what are factors of negative 6? What things multiply to make negative 6? What things multiply to make 6? 3 and 2. I'm going to make you guys do the other one, 1 and 6. And now, with these pairs, I'm going to ask the question, how can I take these pairs and make this number here? 3 minus 2. So the factors fill in to be x plus 3, x minus 2. If I multiply this back together, I will have x squared plus x minus 6. If I FOIL it out. Factoring is undoing foiling. The denominator is x minus 2. I'm sorry if you had said it and I didn't hear it. Limit x goes to 2. If I have these two factors over each other, what is the same in the numerator and denominator? X minus 2s, those cancel. So this function is really, in disguise, x plus 3. It's x plus 3, but it's not defined at 2. So we have found the function it's the same as. And now, I'm not dividing by 0. So I can plug it in. What do I get if I plug in 2? We are trying to find what we can rewrite the function as. If I look at this as graphs, it was x squared plus x plus minus and x minus 2. Okay. To turn this one on and this one off. Okay, so I've turned g of x into the thing we started with. It looks like a line, but if I hover over 2, it's undefined. But limits, we know, doesn't care if it's undefined there. We can still find the limit. So we found, hey, this is the same function as x plus 3. I've turned it on and you can't, well, now it's on top, but it's still not any different than the purple one. Hover over that spot now. And I actually have a result. It's 5. That's what we're trying to do. We're trying to find the function. That is the wrong notes. We're trying to find the function that's the same everywhere but at that same point. That point where it's 0. Okay, so let's try another one. If I take -3 and I put it into the denominator, what do we get? 0. We can't divide by 0. So I want to find the function that this is in disguise. I want to try to factor x squared minus 9. Was it said or?
Not factoring.
Factoring. It's going to turn into x minus 3. X squared minus 9 factors into by the difference of squares or by the route I just told you guys. It factors into x minus 3, x plus 3. The thing that cancels the x plus 3's. We're left with the limit as x goes to -3 of x minus 3. Plug in -3 and we get -6. And we found that limit by canceling it out. So, strategy, there's going to be certain, well, one, recognize the limits that we can just substitute into. That's basically going to be, as long as we're not dividing by 0, we can substitute in. When the limit cannot be evaluated by direct substitution, we want to try and find something that agrees. And then 3, use a graph or table to reinforce there is a way to check our answer. Look at a graph, look at a limit, look at a table, see if those things from Wednesday agree. Now, sometimes factoring doesn't work. So there are some strategies that come up a lot. So first, strategy. Well, we can't. And add what? I get 0 and the denominator can't happen. The strategy here, if we see a square root in the numerator, what we want to do, I'm going to give some big words and then explain what they mean. Multiply top and bottom by the conjugate of the numerator. The conjugate of the numerator is the same numerator, but with the sign in the middle, and so this one changed. So this is a minus. The conjugate is going to be the square root of x plus 1 plus 1. So we're going to multiply by square root x plus 1 plus 1 over square root x plus 1 plus 1. The numerator, when I do that, I'm going to write it out on the side here. When I FOIL, first, square root x plus 1 times square root x plus 1. That give us just x plus 1. The square roots cancel. Outer, square root x plus 1 times 1. With square root x plus 1. Square root x plus 1 times negative 1 is our inner. So we have minus square root x plus 1. And then negative 1 times positive 1. Negative 1. Combine like terms, what do we get left with? X plus 1 minus 1, which is also x. Reason we multiply by the conjugate is the square roots disappear. Those square roots went away. The problem child in this problem, we got rid of. The square roots were our issue, well, was part of our issue. We got rid of them. The numerator is now just x. So I'm going to erase that because I am out of room. But the numerator becomes just x. And the denominator becomes x times the square root of x plus 1 plus 1. Anything cancel? I have a x and an x being multiplied. Those can go away, leaving us with the limit as x goes to 0 of 1 over the square root x plus 1 plus 1. Now what happens if I plug in 0? The denominator's not 0 anymore. Some math magic happened. Now I can plug in 0. What happens in the denominator? What does that become? 2. And so I have 1 over 2, or 1/2 as the limit. And this worked by this theorem. We didn't actually change the function at all. Not technically. We multiplied by 1. A fancy one, but 1. We just multiplied by something that got the divide by 0 to go away, and also got our square root in the numerator to go away. So it helped us out. A secondary strategy for other things that we might see. Suppose I see the limit as x goes to 0 of 1 over 3 plus x plus 1 over 3, no, minus 1 over 3, all over x. What happens if I plug in 0? Bad things. The denominator is 0. I believe the conjugate trick can also work here, but there is a second one I want to look at, and that is combining these fractions first. So how do I subtract fractions? Common denominator. What would be the common denominator between 3 plus x and 3?
3 over. Or x over.
If I had like 1/2 plus 1/3, what would the common denominator be with that? How do 6 and 2 and 3 relate with each other? They're multiplying each other. So the common denominator between 3 plus x and 3 is 3 times 3 plus x. I heard a 3 over, maybe you meant times, but the denominator will be 3 times 3 plus x here. And we multiply by the opposite denominator. So 3 plus x, the opposite denominator is the 3. So let's multiply by 3 over 3. 1/3, the opposite denominator is 3 plus x. And so we get, I need my limit still. Limit, x goes to 0. 3 times 1 over 3 times 3 plus x will become 3 over 3 times 3 plus x. Minus 1 times 3 plus x. 1 times 3 plus x is 3 plus x. Now that there's a common denominator in the top, how do we combine those? So we get a common denominator when we add. So now that we have a common denominator, how do we add the fractions?
3 minus x times 3 plus x in the denominator, right?
3 minus x.
Or can you do that?
Looking back at this one, what would that add together to be?
1.
5 over what?
5 over 6.
The denominator stays the same once we have a common denominator. So this is gonna stay. Oh, I wrote x. Oh,
Yeah,
well, that was what you're trying to point out.
Yeah,
Thank you. I misinterpreted. Thank you. But same thing. Now we just add across the top.
x.
It's just x. Oh, hold up. Yes.
Negative x.
Negative x. Why?
5 because the negative distributes.
The negative distribute. So we end up with a negative x. Limit x goes to 0 of negative x over 3 times 3 plus x all over a big X, or I'll call it x over 1. How do I divide two fractions?
Reciprocals.
Reciprocal. Specifically, what is reciprocal?
Just the fraction upside down.
Which fraction is reciprocal? Because I have like 4 fractions here. The bottom one, the x over 1. I know what a reciprocal is, thank you. Negative x over 3. Times the bottom one flipped. What cancels?
The x.
The x's, the x on the top and the x on the bottom. And I get limit as x goes to 0 of -1 over 3 times 3 plus x Math magic, if I plug in 0, is that denominator 0? No. So what is our fraction? -1/9. So second, if we see a square root, we can evaluate by multiplying by the conjugate. If we see fractions, again, I believe multiplying by conjugate works, but you can also use fraction, common denominators, and simplify things out like we did here. So use common denominators. Next, limit theorem. If h of x is less than or equal to f of x is less than or equal to g of x for all x in an open interval containing c, except possibly c itself. And if the limit of h of x as x goes to c of h of x is L, and that's the same as the limit of g of x, then the function in the middle will also have the same limit. This one is 1. That feels, once we see a picture, kind of straightforward, but it reads weird. So here is my xy plane. Let me call this one g of x. And let me call this function h of x, and maybe we pretend that those actually meet in the middle. And then this setup says f of x is between them. I don't know exactly what f of x is doing, but it's staying between that red and green line. So staying between the red and green line can be real funky, but it stays in here. Let's say here is C. This theorem says if g of x, its limit is L, and h of x, its limit is L, then the really funky one also has a limit of L. It's called the squeeze theorem, as we're squeezing f between the two functions. And if the top thing has a limit and the bottom thing has the same limit, the middle has to have the same limits. And this actually gets us some really unique limits come from it. Some special limits. Some common ones, the limit as x goes to 0 of sine of x over x is 1. The limit as 1 of 1 minus cosine x over x is 0. And the limit as x goes to 0 of 1 plus x to the 1 over x is e. I wrote this one in a different form when we first learned e, but I basically wrote that limit for e with a few variations. So, want to look at trying to show this really famous limit of the limit as x goes to 0 of sine of x over x is 1. So, when I look at my unit circle, what part of the coordinate does sine tell us? The y coordinate. Yes. So I'm gonna draw this in as close as I can. This is gonna be sine of x. Let me try that again. Sine. Sine of x. Is that orange? And when we first started talking about radians, it was when the radius is 1, this is the measure of the angle, this arc length. And so this black arc length that doesn't really stand out against the purple, but the arc length is x. And so if sine is just the straight down distance and x is the curved distance, which one's bigger? The curved. So near 0, sine of x is less than x. And additionally, if I divide everything by x, sine of x over x is less than or equal to 1. Now, we have an upper bound on the sine of x, and really like to make a lower bound on that same sine of x. So, a but so then similarly, what does the graph of sine look like? Okay. Like this. Here's sine. Cosine looks like what? This one. So near x, sorry, near 0, which one's bigger? Cosine. Near 0, cosine is higher than sine. So near 0, cosine x is bigger than sine of x. If I divide this by x, remember x is still bigger than sine. So if I divide by something bigger than sine, like 1 over 2, my fraction gets smaller. If my denominator is bigger than my numerator, my fraction gets smaller. So if I divide this by x, cosine is still bigger because dividing by a bigger number keeps my number getting smaller. So cosine is bigger than sine x over x. And if I reciprocate both sides, I get 1 over cosine and x over sine x. Now, which one's bigger when we reciprocate? Sine. Okay, so we get 1. we are getting far enough on this. I actually want to come back because I think I made a statement there that I want to correct. Because we want to get that sign of x over x. But what we want to do, we're going to take a little bit more than 3 minutes. But if we want to get sine of x over x between two functions, and in doing so, use this fact. Okay. So we will actually come back to finish that out. On Monday, we have very few limits left once we have this one. And then we'll pick up with 2.4. So we have most of our limit rules. Actually, we kind of have all of them. I just want to finish showing this. So back to I don't have them up anymore. Announcement wise, if you hadn't gotten homework, make sure you do so. Homework 3 is posted. 3 problems are from what we have talked about thoroughly already. And then we are a little over a week away from the first exam, so make sure you're working through those problems. If you have any questions, let me know. Have a great couple of days. See you Monday.
I don't know if I'm gonna get those problems done. Sorry. I got a question. So earlier when we were working through the bunch of the limit problems, we wrote limit down every single time. Is that a must? Okay. I was just wondering.
Because it's one of those, if you drop it, you're talking about something different.
All right. So like if we don't throw that in our work, then it will be.
Yeah, you may still get a majority of points, but there will be docking if it comes where it should, if it comes off before it should.
That sounds fine. Thank you.
Yeah.
All of them. All of them. The fact that I believe him too, he'd be the person who finds every combination. 5, 6, 7, 8, 9, 10. No. 1, 2, 3, 4, 100 times. Did you see what I'm going to make my password? Dude, no, you do that. You have the.